We're now starting our next section of Chapter 10, where we're moving from sequences to series. In this section, we're going to be dealing with infinite series, specifically focusing on the geometric series. We're going to begin our discussion of the infinite series with geometric series. These are more common than any other infinite series, and they're also used in many practical problems and problem solving. And they illustrate all the essential features of infinite series in general. Recall that every infinite series has a sequence of partial sums, right? It's a sum of a sequence. And so, for example, S sub 1 is equal to the sum of the first member. S sub 2, the partial sum, is the sum of the first two members, and so on. And so S sub n is the sum of the first n members. If the sequence of partial sums converges, that is, the limit as n goes to infinity of S sub n equals L, then the value of the infinite series is also L. If the partial sums diverges, then the infinite series also diverges. In summary, to evaluate an infinite series, it is necessary to determine a formula for the sequence of partial sums, which we call S sub n, and then find its limit as n goes to infinity. As a preliminary step to geometric series, we're going to study geometric sums, which are finite sums in which each term in the sum is a constant multiple of the previous term. A geometric sum with n terms has the form S sub n equals a plus a times r plus a times r squared dot 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 all the way up to a times r to the exponent of 1 less than r. Okay? Which of course this equals the sum from k equals 0 to n minus 1 of a times r to the k, where a does not equal 0 and r are real numbers, and r is called the ratio of the sum and a is its first term. If we look at an example, if we have r equals 0.1 and a equals 0.9 and n equals 4, we're looking for 4 terms, we get a 0.9 plus a times r 0.09 plus a times r squared, which is 0.009, plus a times r cubed, which is 0.0009, and r cubed, we can see, is 1 less than the number of n. And here we have all of those just done. A times r plus r squared plus a times 1 plus, I guess you could say, r to the 0 plus r to the 1 plus r squared plus r cubed. And you get this summation here. Our goal is really to find a formula for the value of the geometric sum. Your book, and also there's a video that I've embedded in your homework for this section that explains geometric sums in series, that goes through the text, explains how they come up with this formula. It's quite clever. Doesn't take long. It's probably, you can read it in about 2 or 3 minutes. You can watch it in about 5 minutes in that video that's embedded in your homework, etc. But bottom line, our basic formula for a geometric sum is a times the quantity of 1 minus r to the n over 1 minus r. Okay? And when I look at this, I kind of validated it. You can validate it by finding the fourth member of this geometric sum and seeing if this does indeed calculate to the same value, 0.999. Okay? All right. So when we take the geometric sum, it's a short leap to the geometric series. Remember, the geometric series is an infinite series, so all we do is apply the limit as n goes to infinity of the geometric sum. Okay? So our geometric series is from 0 to infinity of a r to the k. So this is the limit as n goes to infinity from k equals 0 to n minus 1. Okay, so we're going from k equals 0 to infinity, but we know that the formula, the general formula, which we just saw, is a times 1 minus r to the n over 1 minus r. So we apply the limit to this formula, and this gives us the geometric series formula that we can then manipulate and use. So we need to come back to the concept of geometric sequences for just a second. In order to compute this limit that we just found in the last slide, the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r, we need to examine the behavior of r to the n as n goes to infinity, because this is going to affect what the value is of the geometric series. So let's remember back from section 10.2, geometric sequences, what specifically is happening with r sub n when n goes to infinity based upon different values of r, when r is less than, the absolute value is less than 1 or a fraction, when r equals 1, or when r is greater than or equal to -1 or greater than 1. Excuse me, less than or equal to -1, or r is greater than 1. So the first case is when the absolute value of r is less than 1. Well, if we apply the limit to the formula, notice the limit really only affects this one term, which is r to the n, because everything else is a constant. A is a constant, r is a constant. It's just this r to the power of n as n goes to infinity. And remember that when the absolute value of r is less than 1, and this is a fractional value like 2/3, etc., between 0 and 1, we see that that value of the limit as n goes to of r to the n, if r, the absolute value of r is less than 1, equals 0. So we plug that in there, and we simply get a times 1 over 1 minus r, or simply a over 1 minus r. And so what this means is that if r is a fraction, or the absolute value of r is less than 1, a fraction less than 1, then we have convergence for this geometric series to the value a over 1 minus r. The other two cases, if the absolute value of r is greater than 1, which is the third case, notice that limit doesn't exist. So as we apply the limit up here, this term doesn't exist, and so this whole this limit doesn't exist, and so we say that in that case the series is going to diverge. There is no limit. It just gets bigger or oscillates, etc. And then the last case, case 3, is when r equals 1, and this is the absolute value of 1, so it could equal positive 1 or negative 1, and this is one place where it's a little bit different. We can see if r equals 1, then every power on r is going to just make that still 1, so we're just going to have a plus a plus a plus a, which of course diverges because it just keeps getting larger and larger. If r equals -1, well, then we have a times this -1 to the power of k, right? And remember, all this does is that since r is negative, when the exponent is even, it's going to be positive. When the exponent is odd, it's going to be negative. And so what we're having here is an oscillation that oscillates between 0 and a. And so we have another table or theorem, Theorem 10.7, kind of summarizes this. So if r is less than or equal to -1, it diverges. If r is greater than or equal to 1, it diverges. But if r is a fraction between -1 and 1, then we have convergence, and based on that formula, a divided by 1 minus r. Okay? So that was a mouthful. You might want to review that again. There's that video that I talked about watching before for the formula goes into this as well. So let's look at our first example. Example 1, geometric series. Evaluate the following geometric series, or state that the series diverges. So if it converges, find the value, and if it doesn't, then just state that it diverges. And I left the Theorem 10.7 little chart up there to the right so that can help you figure out what's happening. So I would like you to go ahead and hit pause. These are pretty straightforward, and go ahead and solve what's going on. Okay? In this first one, it's a little confusing because we're looking for a times r to the k. I guess in this case we'd have a equals 1 and r would be 1.1. Well, if r is greater than 1, then the series diverges, right? So that one was pretty straightforward. Okay? Now in B, we have a little bit different case. We have e to the negative k, and so you might think that r is e, or Euler's constant, raised to the power of k. But remember that negative k, a negative exponent means the reciprocal. So really what we have here is 1 over e to the k, or the fraction 1 over e in parentheses to the k, which is then a fraction. That's 1 over 2.78. So now here we can figure out what the limit, the convergence is, using the formula a over 1 minus r. And again, r is 1 over e, so we get 1 over e in the numerator. Sorry, the a is 1 over 1 minus e, 1 over e, which is the same thing. I guess they just wanted to make this into a simple fraction instead of complex, but you could easily do this in your calculator and come up with that same value without simplifying it first, okay? The big thing here was just recognizing that the negative exponent means this is 1 over e to the k, or 1 over e to the k. Therefore, the ratio is 1 over e, okay? And because it's a fraction between negative 1 and 1, then we can apply the rule that the geometric series converges at a over 1 minus r. Okay. Now the last one looks pretty straightforward. We can see that r, the value, the ratio raised to k, is negative 0.75. The negative inside doesn't have anything to do with the exponent, except we know that it's going to oscillate. The problem here is that it looks like it's going to oscillate, but even oscillating numbers can sometimes converge, so we don't know for sure. When you look at this problem, it looks like a is equal to 3 and r is equal to negative 0.75, but that really doesn't work out because the first term, remember, is always a for a geometric sum. And since this sum, it's already got the limit going all the way to infinity, since this sum starts at k equals 2, then our a is going to be 3 times negative 0.75 squared. And so that's a little, this is math teachers throwing you a little wrench in a problem. So indeed, r is a fraction between negative 1 and 1, but in this problem you have to figure out the value of a, and remember a is always the first term in the geometric sum, and the first term is going to be when k equals 2. And so we can simplify this to a, which again is 3 times negative 0.75 squared, that first term, when you plug in 2, all over 1 minus r, and we get 27 over 28. So these B and C were a little bit tricky, but they are good example problems so that you kind of evaluate these things with a little more focus and attention to detail. So this is an interesting problem. I wasn't going to include it, but I think the solution to this problem is quite interesting and a clever way of doing it. And so I wanted you to see the solution in here, how it came about. And you can hit pause and try this if you want, or you can just watch along. So it's asking you to write this repeating decimal as a geometric series and express its value. So if we think of this decimal, we can see that it's got 1.035, and then it adds another basically 3, 5 after each term. So we can think of that, that 3, 5 with 2 more decimal places as really the geometric series. So if you think about it like this, where the first term is 1, well, actually, let me rephrase that. We have 1 plus a, which is 0.035, and then we want to multiply that by something that gives us the 3, 5, but in the 4th and 5th decimal place. So notice we have to move it over by 2 decimal places, so r would become 0.01. So what's key here is to notice that in this case we have 1 plus a geometric series. This whole thing isn't the geometric series, but just the expansion of the decimal place, okay? And so if we get that, then we can see that since we want it as a geometric series, and since r is a fraction between -1 and 1, then this geometric series is going to sum to a times 1 minus r, sorry, a over 1 minus r, not times, 1 plus a over 1 minus r. This is the value, the convergence of the geometric series since r is a fraction. So we get 1 plus a, which is 0.035 over 1 minus r, or 1 minus 0.01, which equals 205 over 198. So I just thought this was a clever problem. I don't know that I would have you do something like this. I think it's a little bit gamey. It's more like a puzzle than an actual understanding of the concept, but it's a quite clever application of the concept. So we're about halfway through the lecture, and I thought I'd try something different. This is one of my favorite poems by American poet Mary Oliver. She's very pragmatic, and it's a wonderful poem about either when we're in a hard spot in life or when we're trying to make a change, which I think is generally true of most college students, that they're trying to make a change. And here I'm going to allow Chris Tile. This is a recording from YouTube. Chris Tile reads The Journey by Mary Oliver.
This week, a legendary poet moved on from this plane, Mary Oliver. Mary Oliver. Her work was accessible and invitational and expansive. She took the time to explore and reveal the magical world hidden from all of us in plain sight. Her passing is aptly marked by her numerous words that play with our fragile mortality, such as the often quoted, "Tell me, what is it you plan to do with your one wild and precious life?" Here in the cradle of some of our finest centers of higher learning, we'd like to share The Journey by Mary Oliver. One day you finally knew what you had to do and began. Though the voices around you kept shouting their bad advice, though the whole house began to tremble and you felt the old tug at your ankles. "Mend my life," each voice cried, but you didn't stop. You knew what you had to do. Though the wind pried with its stiff fingers at the very foundations, though their melancholy was terrible, it was already late enough, and a wild night, and the road full of fallen branches and stones. But little by little, as you left their voices behind, the stars began to burn through the sheets of clouds, and there was a new voice, which you slowly recognized as your own, that kept you company as you strode deeper and deeper into the world, determined to do the only thing you could do, determined to save the only life that you could save.
So that's a really powerful poem to me, and this picture that you see on the left is me on the north coast of Ireland at a place called North Park Bay in Northern Ireland, actually. And if you ever get a chance to go there, this is a wonderful hostel that I stayed at on the top of a cliff in a very difficult time in my life. And in the middle of the night, I woke and felt compelled to kind of go outside and to go to the beach, which was walking down the cliff. And I've never had such a experience like this before, but it really, the poem came to me, and that night is magical in my life, and it will always be. In this place, North Park Bay, will always stand out for me. Anyway, I hope you enjoyed the poem. You can always move to the next slide, but take a good break and then continue on. With geometric series, we carried out the entire evaluation process by finding a formula for the sequence of partial sums, and then evaluating the limit of this sequence. Not many infinite series can be subjected to this sort of analysis. With another class of series called telescoping series, it can also be done. A telescoping series is any series with terms that cancel out with each other. It's called telescopic because part of each term is canceled out by a later term, collapsing the series like a folding telescope. This kind of series doesn't have a set form like the geometric series did, a over 1 minus r to find the series, or a p series. So in this one, you have to actually do the work. You have to actually find a formula for the sequence and then apply the limit. And that's what we're going to do next. So let's look at example 3, solving telescoping series, okay? So evaluating the series means see if we can find a value that they converge to. And remember that we're going to do this similar to geometric series in that we're going to find the partial sum first and then find a formula for that and then apply the limit as n goes to infinity. Well, the partial sum of both of these telescoping series would just be from k equals 1 all the way to n. So the nth term of this first sequence of partial sums would be from k equals 1 to n of cosine 1 over k minus cosine 1 over k plus 1. Not a big deal, okay? What we're going to want to do is to look at some of the first members of this and kind of get a sense of what's happening. Remember that telescoping series, a lot of things cancel out. They collapse down. So if we go through a few series, we get, when k equals 1, we get the cosine of 1 minus cosine of 1/2. When k equals 2, we get the plus the cosine of 1/2 minus the cosine of 1/3, etc., till we get to the cosine of 1 over n minus the cosine of 1 over n plus 1. If we regroup the terms, we can see here we have a negative cosine 1/2 and a positive cosine 1/2, which equals 0. And that would continue on all the way until the very last term. We'd have the negative cosine 1 over n, positive cosine 1 over n. And so the only two terms that are left are the initial term, the cosine of 1, and the last term, which is minus the cosine of n plus 1, right? The last term would be substituting n for k. So this simplifies down to the cosine of 1 minus the cosine of 1 over n plus 1. That's the partial sum. To find the series, all we have to do is apply the limit as n goes to infinity of this partial sum, which already simplifies down to its collapsed telescope, if you will. So if we apply the sum as k goes from 1 to infinity, this is the same thing as the limit as n goes to infinity of s sub n. So we can apply the limit here, and we can see that when n goes to infinity, we have 1 over infinity, or 0, and the cosine of 0 is 1. So this simplifies down to the cosine of 1 minus 1, or negative 0.46. Okay? Now, you may not have hit pause, and you may have, I didn't even say it, I don't think, this time. And the second one's a little more complex because the index starts at 3, okay? So when we're looking at the next problem, part B, we really want to, let me rephrase that. Because the initial value of the index is k equals 3, the nth partial sum involves n terms that run from k equals 3 to k equals n plus 2, which is somewhat awkward. The nth partial sums are most easily written when the initial value of the index is k equals 1. So we're going to re-index the original sum by using the substitution j equals k minus 2. And then notice what happens here. We now have a partial sum that's equivalent by just substituting in k minus 2 equals j. Well, if we get that, then k minus 1 is going to equal j plus 1. Okay? All we're doing is substituting in this j equals k minus 2. So when we do that, we get an initial index of 1 to infinity. Now this is a good time for you to hit pause and see if you can figure out the rest of it. That indexing part was a little bit confusing, but I think it's, now you can figure out this problem, okay? The variable used as an index does not affect the value of a series, so it's permissible to return to the index k. And that's what we did here, just so it's not confusing. It doesn't matter what you use, if you use j or k, whatever. Okay? So we can see now that S sub n, remember that S sub n is simply taking this series and finding the partial sum from 1 to n. So if we do that, we get S sub n equals the summation from k equals 1 to n of 1 over n times n plus 1. Or I'm sorry, that we can just leave that. If I use k there to n, I misspoke. So S sub n equals the summation from k equals 1 to n of 1 over k times k plus 1. Okay? That's this part here. And typically we'd like to separate these out, 1 over k and minus 1 over k plus 1, so that we can see what's happening with the members, etc. It's a little bit easier that way, and it's also easier typically to apply the limit as n goes to infinity. So again, what we're going to do is we're going to expand this for a few members and kind of see what's happening in the process. So when k equals 1, we get 1 over 1, which is 1, minus 1/2. When k equals 2, we get 1/2 minus 1/3. And again, then we get 1/3 minus 1/4, all the way up to the last term when k equals n, we get 1 over n minus 1 over n plus 1. Excuse me. So here again, if we regroup these, we see we have a negative 1/2 and a positive 1/2, a negative 1/3 and a positive 1/3, etc., until the only terms that are left are the first and the last. So we get S sub n, the partial sum, is equal to 1 minus 1 over n plus 1. Here again, we're going to apply the limit as n goes to infinity of that partial sum. And so we get the limit of 1 minus 1 over infinity plus 1. Well, 1 over infinity goes to 0, and so we're just left with the value of 1. Okay? So this one was a little more confusing because we had to change the index, and you have to kind of figure out how to do that, and it's not really that big a deal. And you got some extra problems to practice there. So next we look at some general properties of convergent series. Before we begin, I want you to know that this summation of a sub k without any limits of like k equals 1 to n, etc., just refers to a general infinite series whose terms may be positive or negative or both. Okay? So suppose the summation of a sub k converges to a and c is a real number, then the series, the summation of c times a sub k, converges, and it equals the coefficient times the summation, the infinite series of a sub k, which simply equals that coefficient times a. And so this is very similar to what we know about derivatives and integrals, that if we have a constant coefficient, that we can pull that constant coefficient out and then multiply the answer at the end from whatever we're doing, differentiating or integrating. So that works here as well when we're looking at convergent series. If there's a coefficient in there, we can pull it out, evaluate the series, and then plug it into the final answer. That's if it converges. If a series diverges, then any kind of coefficient times that also diverges for any number that's not zero, for any coefficient that's not zero. If we're looking at two different infinite series and one of them converges to A and one of them converges to B, then we can, the infinite series of their sum or their difference, it's again just like a derivative. Then we simply can add or subtract the infinite series convergences of each one, etc. So if it's the infinite series A plus the infinite series B, we add their values. If we're subtracting the two infinite series, then we subtract their values. Again, very intuitive. And again, as we saw in step 2, if either A or B diverges, well, actually, I'm sorry, if A diverges and B converges, then the series, the sum of the series or this differences diverges. And so this is really a general statement. If one series diverges and the other converges, then the sum or the difference diverges. Okay? If m is a positive integer, and here we see we're going from k equals 1 to infinity, or k equals m to infinity, so we're talking about an integer other than 1, either both of these series converge or they both diverge. What this is just saying is it doesn't matter where you start. In general, whether a series converges does not depend on a finite number of terms added to or removed from the series. However, the value of a convergent series does change if non-zero terms are added or removed. Okay? So let's look at our final example from the problem. Using property of series to evaluate series. Okay, so hit pause if you can, and then look at those properties of series. Again, they're pretty intuitive, and see if you can solve these two infinite series problems. Okay, hit pause, try it, and then come back. When I look at the first series for part A, I can see that they're both I just went blank, sorry about that, geometric series, right? We can rewrite these as fractions with the exponents outside of parentheses, etc., and this could be a coefficient. So when we're looking at this, we need to evaluate both of these geometric and see if the R value, the ratio, where it is greater than 1, equal to 1, or less than 1 is a fraction. Okay? So I can see that this first one is 1 over 3 to the k. So that's quite clear that the ratio is 1/3. Okay. When I look at the second one, if I pull out the 2, which they've done here, then I have 1 over 3 to the k plus 1, which again is a geometric series with R equaling, the ratio equaling 1/3. Since both of these are they're fractions less than 1, then both of these series converge, and so we can calculate them out. Now the first term in this first one, again, notice our index is k equals 2, so we need to plug that in. 1 over 3 squared is 1/9. Here we have 1 over 3 to the 2 plus 1, which is 3 cubed, or 1/27. Okay, R is the same in both of them, so we can use our formula A over 1 minus R to find the value of the first infinite series, geometric series. And then the second one, we will use a over 1 minus r, but notice we also have a coefficient in it there. And so this is a lot of steps, but here is a over 1 minus r. Here is 2 times a over 1 minus r, and then when we do the math, we get 1/18. Okay? All right, let's look at our next problem, B. So, again, we know that we can separate these into two series. The infinite series value of the first minus the infinite series value of the second. Immediately, you can see that if we pull the 5 out in front, we have the first series is a geometric series with r being equal to 2/3. Well, actually, we'd probably have to pull the 2 out too. I don't know that we need to do that, but this is definitely if it's 2/3 or 1/3, we know that r is less than 1, so the first series is going to converge. The second series is a little more complicated, and so we need to figure out what's going on there. Well, the first series is pretty straightforward. Again, if r equals 2/3, the first member will simply be 5 times 2/3 to the 1 power, I guess they just put that there. And so a over 1 minus r is easy to calculate, and we get the value of 10 for the first series. Now the second series, we have to figure out what's going on, and so a good way to do that might be to just plug in some values there and see what's happening, okay? If we write out the first few terms of the second series, we see that it too, oh, it is a geometric series. I didn't get that. Notice what happens here. When we plug in the first one, we get k minus 1 is 0, so we get 1/6, and then 7 over 6 squared, and then 7 squared over 6 cubed, etc. So we do have a geometric series with r being equal to 7/6. So since r is equal to 7/6, that's greater than 1, and that series diverges. And because one of the series diverges, remember that if either of the series diverges, then the sum or the difference will also diverge. So in this problem, we have a divergent series altogether. Okay?